Welcome to topic 6 of module 2. Here now we will dive into the case studies and we will see that how the engineered time series features are used to perform anomaly detection. Primarily, I want to recap this thing. We have two types of anomaly detection. So we have novelty detection and we have outlier detection. Now, the novelty detection is that if the data does not contain an anomaly or has anomalies labeled, so we can remove them. This is a type of novelty detection. Outlier detection, on the other hand, is more insensitive to small deviations that will hurt the quality of the trained model. So, in outlier detection in the dataset, we can have the anomalies which are already present as well. And this is another important step in the anomaly detection is to remove the anomalies, which is sometimes very laborious and downright impossible task because we have to clean the dataset with the anomalies. Now, when we see it in the security, so there are 5 methods that are available. So we have forecasting, which is a type of supervised machine learning. We have statistical metrics as well, which will see that how to remove anomalies within a data set. Then we also have unsupervised machine learning, goodness of fit and density based methods for anomaly detection. Forecasting is the process of learning from prior data and making a prediction about the future. It looks at the substantial deviations between the forecast and observations as anomalous. So anomaly detection algorithm uses the past data to predict the future values. And if the predicted value is not within the realm of the previous one, this is considered as an anomaly. It measures how different the currently observed data is from the prediction. Forecasting actually lies in the realm of supervised machine learning because we train the model with the previous data. These are the 3 main terms with reference to the time series. So we are talking about trends, which are long-term direction of changes in the data. We are talking about seasons, which are periodic repetitions of the patterns in the data. And we are talking about cycles, that are data that have pattern similarities, but they vary in periodicity. So they are not very consistent as per the time. So forecasting learns the characteristic of the time series by looking at the previous points and making predictions about the future. And it performs autocorrelation as well. That is the correlation between the series and itself at a previous point in time. A good forecaster of the series can be thought of as a future point having high autocorrelation with the previous points. Now we study the first algorithm, which is ARIMA, Autoregressive Integrated Moving Average. It provides a powerful and flexible way of performing forecasting on time series. It is actually a set of autoregressive models. So the output that are linearly dependent on their previous values in combination with a stochastic factor. Seasonal ARIMA, on the other hand, define a seasonal or non-seasonal component of the ARIMA model, allowing periodic characteristics to be captured. So we look at the periodic characteristic, like in this time frame, if this spike hike was coming in the series, what exactly is the reason? So ARIMA uses a distributed lag model in which regressions are used to predict the future values based on the lagged values. And it has 2 very important parameters, the autoregressive and the moving average parameter that are used to tune the model. And it also has a polynomial factor differencing, which actually compares the new values with the previous time series values. Now, if the differencing order is used to make the series more stationary. So if, for example, the differencing order is 0, so the series is stationary. This means there is no change. And if the change is going downward, the differencing order will be upward or downward will be having 1, which is steadily, which means like very small change. But if the time series has a lot of difference from the previous values, the differencing order will be 2. The implementation of the ARIMA is make in Python, and we have done like the case study that is being shown. It has an auto-regressive order of 11, moving average order of 11, and differencing order of 0. We perform the in-sample training set on the ARIMA, and then we also perform out of sample as well. So we try to see that how ARIMA perform on out of sample implementation. Let's take a look at the Python implementation in the Google Colab for ARIMA.